was going to say good afternoon because I just flew from DC area. It's 1:56 there. It's good morning here. Good morning once again. My name is Samet Ayhan. I'm with the University of Maryland. This research pertains to aircraft trajectory prediction with predictive analytics. This research is being carried out by myself and my advisor, Professor Samet at the University of Maryland. I have another hat with the Boeing Research and Technology, but I'm not wearing that hat here. So I'll go ahead and motivate the problem and then set the stage with a number of definitions, not a whole lot, and then I'll state the problem, and then I'll discuss our approach to aircraft trajectory prediction. Then I'll share with you our evaluation results, and we'll conclude, and I'll talk about the future work. At the end, we'll have a Q&A session as usual. Let's go ahead and take a look at how substantial it is predicting aircraft trajectories. Just keep in mind that at any given time, there are about 6,000 aircraft in the U.S. airspace. As we talk right now, there are about 6,000 aircraft in the U.S. National airspace. 837 million passengers are served each year, and 61 billion pounds of cargo carried each year. And the impact of civil aviation industry to the U.S. economy is as follows. It contributes about 5.6% to the U.S. GDP. It supports about 12 million jobs, and it accounts for $1.5 trillion in total economic activity. So it's a substantial matter, no doubt. Now let's talk about who really handles this matter. Air traffic control is one of them, and air service provider is another one. The goals of the air traffic control is to provide safe and efficient management of aircraft. The ANSP's goal is to provide optimal airspace capacity and efficiency within national airspace. So these goals require separation and sequencing of aircraft using decision support tools. At the core of decision support tools are one of them is trajectory prediction tool, and it's very important because it helps to determine how the airspace is going to look so that better decisions can be made and advisories could be issued. If one ends up with inaccurate trajectory prediction, it would have substantial impact on the performance of DSD, which may result in larger separation standards, increased number of conflicts, inefficient fuel consumption, and adverse impact on the environment. And if you really take a look at all these potential outcomes, you would burn more fuel than necessary. You would jeopardize safety and security, and you would just increase the workload of air traffic controllers. So optimization is a really critical matter here. Now, the prior trajectory prediction research have been able to address the challenge to some extent by performing deterministic trajectory prediction by communicating with the aircraft on a regular basis, which is costly and may or may not really generate accurate results. Dealing with increasingly congested airspace and new environmental concerns still remains the challenge when the deterministic approach is used. For that reason, we take stochastic approach. We will just go over 6 short definitions and then I'll go ahead and state the problem. The original trajectory of an aircraft is a continuous representation of its motion in 4D, latitude, longitude, altitude, time, right? And one is never going to be able to really continuously record that. So what we would do is we would turn into a road trajectory, which is a finite sequence of positions with timestamps. It's kind of resembled. And then we have reference point, which is a fixed spatial location in 3D space that is independent of the trajectory data source. Now the line trajectory is when we use road trajectory to snap those readings to the reference points. That generates a line trajectory. Next definition is spatio-temporal data cube. It's an atomic trajectory unit in space defined by its reference point coordinates, which is the center, and weather parameters that are supposed to be correlated with that position. Definition number 6, and the last one, is airspace volume of interest. You could consider airspace volume of interest as a set of cubes stacked up horizontally and vertically that fills up the entire airspace. That's our approach. Now let's state the problem and see what our approach is. So given a set of historical road trajectories with pertinent weather observations, we aim at learning a model that reviews the correlation between weather conditions and aircraft positions and predicts the trajectories in a form of time series. That's the problem that we're aiming at. We assume weather observations are realizations of hidden aircraft positions, and the transitions between underlying hidden segments follow a Markov model. That's the gist. This assumption considers a finite set of states, each of which is associated with probability distribution over all possible trajectory segments. Right? It's a probability distribution simply. And what we'd like to do is we'd like to come up with an optimal solution that maximizes that overall probability distribution. The states are not visible, but the pertinent observations, which are the weather measurements, weather observations, are visible. So given a sequence of observations, we learn hidden Markov model and derive a sequence of hidden states that map to the sequence of observations. In fact, we all know from NLP and other domains that Viterbi algorithm is an efficient method to compute this. So, but in our problem space, the observation sequence is also unknown, which means that, so overall we know where the aircraft flies based on the historical trajectories. We don't quite know which airspace volume of interest or the data cubes are stacked up horizontally to define the trajectory. For that reason, the very first thing we need to really address is to come up with weather observations that are supposed to be mapping to the trajectory points. In our approach, we define airspace as a set of spatio-temporal cubes, data cubes. Each cube is an atomic unit. You could really consider that like a Lego. You stack up horizontally, vertically, and make up the airspace. And what we're trying to do is, given the fact that we consider these cubes as atomic units, we want to determine, or we want to predict which cubes out of these many to pick, so that once connected to each other, that we could predict the aircraft trajectory. And each cube is an atomic unit defined by latitude, longitude, altitude, temperature, wind speed, and wind direction, along with the time stamp. The weather parameters remain homogeneous within the cube during a period of time, and we'll talk about what the spatial and temporal resolutions are. Our trajectory prediction system follows three major steps. It performs training data processing, which is red colored on this picture, and then test data processing, which is the blue, and then the HMM and HMM processing and Viterbi, which is the green color. The very left are the data sources, road trajectory database as well as weather database. In training data processing, we use Federal Aviation Administration's as the data. Temporally, it's 60 seconds updated recordings, radar recordings. For the weather model, we use NOAA's rapid update cycle product. Its lateral resolution is 13 kilometers. Vertical resolution is made up of 50 levels from ground up. And then its temporal resolution is 1 hour. So the weather observations are recorded once an hour. What we do using the trajectory and weather data is that we perform grid-based alignment, and then we construct 4D data cubes, then we compute HMM parameters. Now here is a visual illustration. As you can see on the very left-hand side, we got the grid network, which is based on the weather model provided by NOAA. In the middle, we have the road trajectory and a line trajectory. Simply, if you look at the grid points, the yellow line follows the grid points, which means that the points on the green one are snapped to the closest, nearest neighboring grid point, making up the aligned trajectory. And this is carried out on 3D. And the next thing we do is we fuse the weather parameters with these cubes so that we have a 4D spatial temporal data cubes. In the next step, we perform test data processing by creating a number of buckets per weather observation, including temperature, wind speed, and wind direction. You can see the buckets here on the right-hand side. We transform the line to historical trajectories by replacing the original date per reference point with the current date. So we treat the historical measurements as if they are current, so that what we could do is we could go ahead and apply time series clustering to determine which cubes out of these could be fed into Viterbi algorithm. As you know, Viterbi requires observations, and in our problem space, the observations are not certainly known. They are unknown. I mean, we approximately do know. Let's consider the case, which I'll talk in detail, that I fly from DC IAD, Dulles Airport, to San Francisco Airport. We kind of know what the airspace is going to be based on the historical trajectories, but we do not know what it may be today. So we need to predict the weather observations first, then find or compute the pertinent trajectory segments. For that reason, we treat the historical observations as if they are current. And then we generate hypothetical data cubes by fusing weather parameters with spatial data. And then we perform, by omitting spatial data, we perform time series clustering. We use KNN with DTW on the weather parameters. It does enforces a locality constraint, and it uses LBQ lower bound. That kind of optimizes and speeds it up. and then we feed all these into the Viterbo algorithm. So the states here are represented by reference points coordinates, which are part of the aligned trajectories. Transition probabilities is the probability of an aircraft transitioning from one state to another. And then the emission probabilities is the probability of weather parameters having been observed at a specific state. So we're simply trying to unfold the correlation between the weather observations and the aircraft positions. And of course, the initial probabilities is the probability of an aligned trajectory beginning at a specific state. And as you can see on the formula, we're all aware that it just tries to maximize the probability distribution by adding a new segment to the trajectory, predicted trajectory. Now let's briefly talk about the evaluation. We used real horse track data along with real weather data. It was flight Delta 2173. We used real horse track data. Plenty of people use Monte Carlo simulation and so on and so forth. But we've used, and it's actually current. Delta flies between Atlanta and Miami on a regular basis with DAL 2173. And the data we looked was between May 2010 to December 2011. And for the trajectory data, we used track data with 60-second update. And then for the weather, as I mentioned, we used a rapid update cycle of NOAA with a lateral resolution of 13 kilometers and vertical resolution of 50 levels, temporal resolution of 1 hour. Data cleaning eliminated plenty of data points. So the historical recordings reduced from 56,000 some points, 37,000 some points. And we ended up computing HMM parameters where we had 3698 distinct states, and we formed transition matrix, and we formed the emission matrix, and the initial matrix where the aircraft really departed was in one of the 28 states. So basically, to maximize, you just multiply and come up with the highest maximum probability distribution overall. The platform we ran all over tests were Intel Core i7 CPU with 280 gigahertz, 16 gigabyte memory. It's just, off the shelf. There was nothing special with that. The results, to come up with results, we bootstrapped by drawing 23 trajectory samples, and we compared our trajectory with the ground truth. And then we computed the mean error and standard deviation, and we rank ordered the means to estimate 2.5 and 97.5 percentile values for the 95% confidence interval. Now here is a qualitative result. As you could see, the data cubes are the ones that we predicted, our system predicted. Those are the white cubes. And the red line is the aligned actual trajectory. Now, by looking at this, you could clearly say that the climb and descent phases are where the problems are. So that's something we've been really working hard to resolve. But overall, when the aircraft is en route, it's quite clear that the results are pretty good. As you could see that from departure to the end of the climb, top of climb it's called, it's okay, but the best is really within this middle area where the aircraft is en route. And then here it's also the accuracy goes down when the aircraft descends to land. Now, if you look at the results, the measurements we used actually were threefold. So this is the first trajectory point, this is the predicted one, this is the actual. So given that, we have used 3 measurements, a long track, horizontal, and cross track errors. And as you can see, we computed the mean errors and standard deviation for all of those, and then we computed, the horizontal error, vertical error, long track, cross track errors on the right hand side as I'm sharing. Now, one more thing I'd like to share with you is error over look ahead time is again confirming our findings that the problem is when the aircraft climbs and descends. In between, we don't see high deviations, I would say. And now the conclusion in future work, our system achieved horizontal accuracy of 12.6 kilometers, which is within the boundaries of highest spatial resolution we used due to the weather data we have. For higher accuracy, we should either use weather observations of higher resolution, which is not available at this time. The NOAA has 3 kilometer by 3 kilometer data available, but that's not operational yet. Another option, which at the time of this paper we were not able to implement, but now we do have it, and we increased our resolution and accuracy, that we performed resampling and interpolation from existing observations, so we achieved really way higher results, and I'll be happy to discuss offline as I'm kind of going over, and I don't want to do that. So, and that's where we stand, and thank you very much for your time.
In your weather features, I didn't really see features that would reveal thunderstorms very well, and thunderstorms are clearly one of the things which can give you deviations of a flight path, especially in the ascent and descent phases, not so much along cruise. Did I miss something, or were you using a relatively weak feature set?
We're using 3 weather observations: temperature, wind speed, wind direction.
Right, from which you can't obviously deduce the presence of a thunderstorm except by looking at the vertical temperature gradient.
So there are actually 20 plus features by NOAA's rapid update cycle weather observations, and per the subject matter expert, these are 3 major ones. And when we really tried to correlate between weather observations and trajectory segments, we did not specifically look at thunderstorm. We generically created buckets of these 3 weather observations only. If any of those really map to under the hood a thunderstorm, that would be correlated by the system by picking the optimal trajectory segment. But here within the weather observations, there's no measure that really maps to thunderstorm, as I could say. But we could talk offline on this.
Okay, thank you.
I worked a few years ago with Air Services Australia, and they had at the time concept of flexible routes, where a pilot could choose a different route from the initial one due to weather and in order to be safe or to minimize fuel consumption if it was the case to have too little fuel. Did you look at relationship between weather and fuel, or weather and safety, or all of them together to use in your predictive model?
So the idea is basically to correlate between the weather and trajectory segments. And the outcome is purely based on the historical data, as you could imagine. So this is really not, this system is not going to provide with a solution that would be superior to what the historical trajectories were traversed. So given that, all we looked was, given these historical weather observations, what would be the optimal set of trajectory segments to predict the trajectory. That was pretty much it. But I work with Air Services Australia using the other hat I mentioned earlier, not University of Maryland's. And yes, I mean, predicting trajectories is a very crucial problem, and people look at it from different perspectives. No doubt.
Yeah.
Thanks for the question.
Yeah, so hi. What exactly do you try to do here? Because commercial navigation is based on VOR, and you're not using those models. So if you fly from here to Seattle, it's basically one of three trajectories. And for weather patterns, they have predefined knowledge models, how to avoid them. And weather patterns are typically, so I'm linking to the first question, only abnormal thunderstorms would be something relevant for predicting, and descent and climb. I'm not even surprised that during cruise you predict, because basically that's pretty trivial. Just take the route planning, and you'll get those results.
Well, let me say this. I appreciate the question. Actually, it feels like we're not in KDD, but in air traffic conference now, because I get really good questions. So, sir, the reason why we're implementing this is to get away from the current flight planning. We do not want to follow. We want to perform what the previous speaker asked. We want to follow something called business trajectories that offers more flexible trajectories.
Then why do you test it on commercial flights? Test it on general aviation or on business flights. Your tests are on commercial flights that basically run a model-based trajectory.
Well, to some extent that's true, but this is an evaluation. I mean, the fact is, getting a number of years of trajectory data for GA is quite challenging. That's one thing.
Okay.
And given the airspace they fly, the class that they fly, and also, with this evaluation, we're just proving that we have something that we could verify and validate by looking at what we've fed into the system and what the outcome was, and by comparing that with the ground truth. With the GA, that would be quite hard, and the addressed business is also quite different. I mean, we're addressing the commercial airlines problems, which helps the FAA as well as the other stakeholders.
Well, the problem of the commercial airlines is to have, if you want to solve that, it's not predicting, it's building plans, right?
I think I could make
your
myself...
Your evaluation is basically choosing, it's trivial. And, just predicting cruise is basically useless. So, did you try to look at something? These, you just take a manual and you can predict these cruise routes.
Probably we can take this question offline. So because
okay.
Time limit, we can leave some time slot for other speakers. Okay. So you guys go
Sounds
discuss
good. Yes,
it.
Thank you.
Please offline. Okay.
Sounds good.
Okay.
Thanks for the question.
So thanks for the speaker. Okay.